In our earlier discussion of what is moment of inertia, we looked at the case where we had an inclined plane, we had a hoop, and then we looked at the same inclined plane, and we had a solid disc. We let them go, and as we let them go, they rolled down the incline, and the disc won. The disc got to the end because both of them had the same amount of gravitational potential energy. Remember U sub G, because they have the same mass, and they were the same height, and they have the same radius. But because all of the mass is concentrated on the edge of the ring, more of the potential energy, more of this gravitational potential energy, was converted into rotational kinetic energy. So we kind of looked at, what does this mean? So let's look at it a little more specifically. So if we look at the amount of energy or the types of energy in the system, like maybe an energy bar graph or energy bar chart, and we have at the beginning, there's all gravitational potential energy. And then at the end, when our hoop made it to the bottom down here, it had some linear motion. We call that translational kinetic energy. That's your regular old 1/2 mv squared. And then it had rotational kinetic energy. Now, we've done this whole analogy thing before, looking at different quantities that we had in linear motion. So, like, remember, force is analogous to torque, and linear speed is analogous to our angular speed, and our linear acceleration is analogous to our angular acceleration. That's the little alpha. So if we look at kinetic energy as being one half mv squared, that is our translational kinetic energy. That means in a straight line. So then our rotational kinetic energy, I'm going to use a little r subscript there, would be 1/2. Now it's not the mass, but the moment of inertia, and it's not the linear velocity, but it's the angular velocity. So this is our rotational kinetic energy equation. Let's look at maybe an example, what that would entail. So let's take the case of a hoop. And our hoop has a mass of 2 kilograms, a radius of 4 centimeters, and the height of our ramp will be 50 centimeters. Now, my question is, what is the translational speed of the hoop at the bottom of the ramp? So let's look at the setup. So here's our ramp with a height of 0.5 meters, and here's our hoop, and it's going to roll down, down, down until it gets here. And even though the center of mass is actually a little bit more than half a meter above the plane, when the hoop gets down to the bottom, when it's down here, its radius or its center of mass will still be above the ground, so that still our net change in height will be equivalent to 0.5 meters. So, energy bar graph, that's a good way to think about energy, before and after. So just like we looked at earlier, before we have all gravitational potential energy. Afterward, now I'm going to give it less translational kinetic energy because I know how a hoop behaves. But, you know, unless you are looking for an exact representation, then you can just kind of make your guesstimation here. This helps you write your equation. All right, so let's do that. So let's start with our gravitational potential energy is equal to our translational kinetic energy and our rotational kinetic energy. So that means that mgy is equal to 1/2 mv squared plus 1/2 I omega squared. So this is where knowing the moment of inertia is important. You don't have to memorize them, but having them kind of in your brain is nice. All right, so let's do some substitution here. And so that means we're going to have mgy is equal to 1/2 mv squared. And I'm looking for this velocity right here. The moment of inertia plus 1/2. The moment of inertia of a hoop is mr squared. Now remember this omega here, v equals r omega is the translation there. So that means that omega is equal to what, v over r? So I can make a substitution here, and I'm going to make it like in another color. So it should be v over r, but all squared because this omega is squared. So now we can actually go back here and divide out by m now that we have taken into account this moment of inertia. So now let's see what we can do. So we'll have g y is equal to 1/2 v squared plus 1/2 r squared times, now that would be v squared over, this is the radius, r squared, so that cancels out nicely there, right? So this r squared and this r squared cancel out there. And then we'd have gy is equal to 1/2 v squared plus 1/2 v squared. That looks pretty good. So now let's combine this. We've got gy would be equal to 1/2 v squared plus 1/2 v squared is just v squared. So then we should be able to find the speed at the bottom. And at this point, we have canceled out the masses, we have reduced the r's, and the speed should be the square root of about 5. And I think that's about 2.23 meters per second. My approximation sign is not very pretty right there. So it's about 2.2 meters per second. So you can analyze the speed of an object based on its moment of inertia. So you can do the same process again, but make it a solid disk, and the moment of inertia would be 1/2 mr squared, and so the speed at the bottom would be different.